sense. So if I put everyone's name in a bin and I pulled it out, we would have a 4 in 7 chance of me pulling out a male's name. All right, then we go over here and it's like, what's the probability of pulling out someone with blue eyes? Now notice it's not specifying girl or boy. It just says someone with blue eyes. What would that probability be? Zach?
2 out of 14.
It'd be 2.
7.
Careful.
It'd be 4 out of 14.
It'd be 4 over 14.
So 2 over 7.
Yeah, 2 over 7, yeah. That just sounded like there was a lot of disgust with your answer, and it was correct. It is 2 over 7. All right, 2 over 7. We got 4 over 7 male. What's the probability of it being a girl? Yeah. Yeah, it'd be 6 over 14 or 3 over 7. And in fact, we're going to get to this in a second. These are known as complements. These are known as complements. They complement each other. Where one is 4 over 7, so the opposite is 3 over 7. In other words, the probability of being a male is 4 over 7. The probability of it not being male is then 3 over 7. So a lot of times we'll call these complements. They complement each other. When you add them together, they equal 1. They're called complements. All right, what's the probability of getting a brown-eyed person? Yeah.
6 over 14, so 3 over 7.
Yeah. Yeah, I like giving me that 6 over 14. It makes our life a little easier to see where it's pulling from. And then we have 3 over 7. All right, probability of another eye color. I'll finish this one. We should have 2, right? Yeah. We should have 2 over 14 or 1 over 7. And then green, just to finish this off, green is 2 also over 14, which would equal, I don't know why I put a 1 out front. It's dumb. We would have 1 over 7. All right, now I want to get to this statement right here, or. Or and. Or has a definite meaning in probability. And I think we would know what or means, but I just want to go over what or means in probability. Or can have 2 different meanings. If you go to a restaurant, they always ask you, do you want a salad or soup? Actually, they usually do soup or salad for whatever reason in that order all the time. Does that mean you get both? No, you get one or the other. That's what we do in probability. It's either one or the other one. The other time we use or is maybe you go to Starbucks and you have coffee. And when you go to Starbucks, you usually don't get just a black coffee. At the very least, they might ask, do you want sugar or cream? Are you allowed to get both? Yeah. In that case, or is not as defined because you can have both. But when we do or in probability, it's always I went out to the restaurant. It's this or it's this. It can't be both. So when we do the first one, it says, what's the probability it's a male or a female? What was that? You have a 100% chance. If I put all your names in a bucket and I'm going to pull out either a girl name or a boy name, that has to be 100%. Now let's break this down a little bit further to prove it's 100%. So this should just be 1. It's everything. When you use the term or, you can actually turn it into the statement probability it's male plus the probability it's female. So or leads to a plus statement. And we said the probability of getting a male, if I randomly did it, was 4 over 7. Plus a female would be 3 over 7. What's 4 over 7 plus 3 over 7? 1. Obviously, it's pretty easy in this case, but in other times you'll have to do that addition. So this would equal 1. Now the next one is, what's the probability of pulling a blue or brown eyes? Once again, that or statement means we can do probability of blue. I'll just do BL. Or the probability Or means plus, or the probability of it being a brown-eyed person. I don't know why this is RR almost. Let's turn that into a BR. Can someone give me the probability of getting a blue-eyed person? Give it to me over 14. Don't reduce it. Elsie? 4 over 14. I'm not looking up there. I'm assuming you're correct. What would the probability of getting a brown-eyed person be? Give it to me over 14 so we can add them more easily. Yeah, Alex. 6 out of 14. So we're doing plus 6 over 14. So that would end up equaling, what, 10 over 14, which would equal 5 over 7. So we'd have 5 over 7. Now, I want to talk about this blue and brown eyes thing. Blue and brown eyes are known as something called mutually exclusive. Blue and brown eyes is known as being mutually exclusive. Mutually exclusive means they cannot occur at the same time. That's an important word. What was that? I'm sorry.
Did you mean to put on the one? Weren't you talking about the end?
No, I'm saying the two words are mutually exclusive.
Oh, okay.
I'm not reading that, yes, this is blue or brown eyes. I get that. But I'm saying the terms blue and brown are known as mutually exclusive. They don't occur at the same time. They could, though. Is that what our hands are up for?
Well, what do you mean by occur?
I mean, in this class, is there anyone that has a blue and brown eye? In this class? No. So they're mutually exclusive in this class. Are there people that have two different eye colors?
Yeah.
So if that person was in our room, this would not be mutually exclusive. This would then become mutually inclusive. Yes?
Would male and female be mutually exclusive?
Male and female would be mutually exclusive for the most part. Because you know the day and age we live in that you might be both or something. But yes, technically this would be our mutually exclusive as well. You're just looking for, do they have a foot in both camps? So does someone have a blue or brown eye in this class? No. So they each occur on their own. Either you're blue-eyed or you're brown-eyed. Our last one says, what's the probability of you being blue and brown-eyed in this class? 0. No one's in there. It's our mutually exclusive. So I'll have to alter this lesson as soon as we have someone in here with both colors. Then I'll have to talk about mutually exclusive. In fact, that leads us to our next statement. Male or blue eyes. Are those mutually exclusive? No. Why? Does someone know why they're not mutually exclusive? Yes?
Because someone can be male and have blue eyes.
They can be male and have blue eyes. The counter to mutually exclusive is mutually inclusive. Honestly, usually we just talk about mutually exclusive. We say things are mutually exclusive or they're not. We don't usually talk about inclusive as much. All right, so that means there are males in here that have blue eyes. So let's talk about this. Let's say I do probability that I pick out a name that's male. Let's make this a little bit up here so I have more room. Probability it's a male plus probability you have blue eyes. Don't write what I'm writing next. You can write this, but don't write what I write next. Because I'm going to change it a little bit. Can someone tell me what the probability it is of being a male in this class out of 14? 8. 8 out of 14. What's the probability of you having blue eyes?
4.
4 people have it out of 14. So this would give us 12 out of 14. There's something wrong with that number. There's something wrong with that number. It should seem off. Bowen, do you know what's wrong with that number?
We don't have that many more.
We don't have that many, right? Alex? Say that again?
So like 14 is like the entire class.
Right.
But we're figuring out males that have blue eyes.
Right, we should still use the 14. We should still use the total. But Bowen's on, so we're using too much, yeah.
We are still accounting for the males with the blue eyes with 4 out of 14, so we got to change it for 2 out of 14.
Yes.
We already counted for the males.
We double counted. We counted males with blue eyes in this category, and we counted males with blue eyes in this category. You cannot double count. That'll make your number too big. In fact, we could have pushed over 100% chance. So we can't just do probability of male plus probability of blue. What Owen said is we could have subtracted it from blue and said 2 over. What I'm going to say is we're going to subtract any overlap that we have. So I'm going to subtract the probability of being male and blue-eyed. That will get rid of all of our overlap that happened twice. So we said the probability of being male again was that 8? I don't want to look up there. Yeah. 8 out of 14. The probability of blue eyes was 4 out of 14. What was the probability of being male and blue-eyed? 2. So that's going to end up equaling 10 over 14 instead of that 12 over 14, which is actually 5 over 7. So we got to be careful if it's mutually inclusive because we have to not double count. We counted it twice. Males with blue eyes were here. Males with blue eyes are here. We had to subtract that I counted them too many times. Does that make sense? It's kind of weird. But does it make sense? We're good. Okay. All right. Female and brown eyes. We can just go to our list. How many females have brown eyes in this class?
1.
1. And that'd be 1 out of 14. All right, let's talk about our complements again. So if I ask you what's the probability of not blue eyes, what I'm probably going to find is usually easier is what's the probability of having blue eyes. And we said the probability of having blue eyes is 4 over 14. If I know the probability of having blue eyes is 4 over 14, what would the probability of not having blue eyes be then? Yeah.
10 over 14.
It'd be 10 over 14. Perfect. They're complements. These two things are complements. Blue eyes, not blue eyes. So if I want to find the probability of not male, it's probably easy there, but usually we're going to think, well, what's the probability of actually getting a male? So we said to get a male, there's 8 out of 14 people. So a not male would be 4. Nope, not 4, 6. Let's be right there, 6 over 14. Or we could have said how many girls are in the class. Because once again, those are mutually exclusive. So we could have just flipped that.
Wait, would it
Not male becomes female.
Would it be 6 over 14 or 3 over 7?
I just left it at 6 over 14 so we can see. I just want to be able to see this difference. So when you go back to your notes and you look at complements, we go with those two. So you may want to note that these are complements. In fact, this is the only time that complements come up in our notes. So just make sure you note that those two things are complements of each other. Yes?
So you make the table with all the data, right?
Yep.
Why don't people just make it a relative frequency table so all the...
So we can have it all done? Well, most of the time we're not going to draw out our sample space.
All right.
For instance, when I tell you to roll 2 die, are you going to want to every single time have to write that entire table down? No. So most of the time we don't do our whole sample space. It happens in our head. And I don't want to have to do a frequency table in my head. Does that make sense?
Yeah.
A lot of times I'll just ask one question. Like I might say, roll a die, what's probably getting a 2 on it? That's 1 out of 6. I don't want to have to write down every possible thing and the percent for every little thing. So you are correct. In that table, it might have been nice and easy to make a frequency table, and we could just pull all that data from there. In that case, it probably would have been easier. All right, so that brings us to simple probability. Simple probability is one event happening. One event happening. I flip one coin, I roll 1 die, I pull 1 card. That is known as simple probability. On Monday, we'll talk about compound probability. That's the probability I roll a die, and then another die. All right, so when we're doing probability, it's the number of ways it can happen over the total number of possible outcomes. So the possibility of me randomly picking a girl in this class was 6 ways it could happen out of 14 possible outcomes. That's when we came up with that 6 over 14. And then we said mutually exclusive events are events that can't happen at the same time. Those are the ones that can't happen at the same time. At the same time. Cool. All right, now let's talk about theoretical versus experimental probability. So the first one we're talking about is theoretical probability. Well, that is the probability that is determined on the basis of just reasoning. Just reasoning. I'm not actually rolling all these die. I'm presenting the sample space, and we're using that information to come up with this probability. So I want to know, what is the probability of rolling a sum of 4 with a pair of dice? First of all, this is my sample space. How many total outcomes are there? In other words, what would our n value be?
36.
It would be 36. What's 6 times 6?
36.
Are there 6 sides on each die?
Mm-hmm.
What if that's something? I don't know this stuff. All right, but that could be a connection. So we're looking at where it actually equals 4, and what I want to point out, do I have a color that can make it show up? Maybe. I have a 4 here, I have a 4 here, I have a 4 here. Is it a coincidence that it's a diagonal? No. Look at any diagonal. So if I come here, this is 6 plus 3, which is 9. 5 plus 4, 9. 5 plus 4, 9. 6 plus 3, 9. All of our diagonals are actually our sums. It actually makes finding your sums really, really quick if you realize that. Logan, let's keep up. All right, so our total possible outcomes that are successful are 3. There are 3 ways that we get a sum of 4. So we're going to do the probability, let's just leave it purple, that I have a sum of 4. Get used to writing these. We're going to practice a little bit on homework, and you'll have to do it on Monday's homework. You have to write it like that. So we have a probability sum of 4 is going to equal 3 out of 36, which equals 1 over 12. And normally we would not approximate this. You can do probability in terms of, I think I wrote it up here, fractions, decimals, percents. We usually just leave it in fractions. That way you don't need your calculator. I need your calculator now. What is 1 divided by 12?
It's 1 over 1.
Thank you. Bowen with the insightful answer. Say that again.
0.08.
0.08. Can I get one more decimal? 3. Cool. All right, we're going to use that because that's our theoretical. 1 out of 12 is our theoretical. Now what we're going to do is we're actually going to do some rolls. I'm going to change these with tens. I'm going to do 10, 100, 1,000. It's just a little nicer. Then we're actually going to do 10,000. Then maybe we'll do 100,000. Who knows? Who knows what craziness is going to happen next? So let's actually roll these die hypothetically. Well, pretty accurately, because we're going to have a little die roll. Is this the right one? Yes, this is it. Give me 1 second. I'm going to roll a die real quick. Okay. So we have 1 die. We're going to roll 2 die. We're going to roll it 10 times. We're going to go. And we're going to see how many of these add up to 4. So make sure I don't miss any. So we have 1. 1. So we got 1. So we can come back here and say that's 1 out of 10. So this one is, maybe I'll put a little block here and say that's 1 out of 10. That would be about 10%. Now let's just put it as 0.1. 0.10. All right, so 10 got us as 0.1. Now, if I rolled the die 100 times, would it be closer to our theoretical? Or would it not matter? Maybe. Maybe. Let's check. Let's go back here. Let's change this to 100 times. We rolled it, and we're looking at the sum over here. It makes it easier, so let me know when we see. I got 1. 2.
4. 5.
So what did we get? We got 5 out of 100. Bowen, what is that percent? 2%? No. You're thinking 5%, I think. Yeah. So 0.5. Are we further or closer? Further. Okay, let's roll it 1,000 times. Oh, yeah. Did I just put 0.5? I'm sorry. I did that with the other one too, didn't I? It should be, I put my zeros in the wrong place. No, I was right on this one, yeah. This one should be 0.05. You're right. Okay, let's roll it 1,000 times. What, did someone say what time is it? All right, so let's go.
1. 2. Did we just ask one? 3. 4. 5.
Did we see 5? I didn't see 1.
4.
Oh! Should we just do that instead? Let's do that instead. Oh, it's already up there as control. All right, so now we just got to eliminate the ones that aren't there. So I have a 4 down here, so subtract 1. Is there another one down there?
Yeah, there's a lot.
Do-
Keep going down. Go down.
2. So there's 2 down there.
Well, you have to just actually scroll.
And there's 4 up there, right? And I have 105 total.
101. No, you have 101. It says it there. Because you got to subtract the...
Yes. So we're going to have 101 within the data. I made the other class do it.
Really?
So we have 101 over 1,000.
Thank you, Owen. Gotta love Owen.
We were going to do it regardless because we're going to do more numbers. So what's 101 divided by 1,000 in decimals?
0.101.
0.101-ish.
So like 10.1.
We'll just do a 0.10 again. Okay, so we're not any closer, so maybe we need more digits.
No.
Let's do
100,000.
1 million.
Let's do 10,000.
I feel like it's gonna be
10,000 minus 4.
So that is 882.
You made them count on these?
No, I didn't do this one. We just did this for the bigger ones.
Oh, but you made them count the 100.
Yeah.
730.
So we have what? 882
1.
over 10,000. What is that in decimals?
0.088.
0.088. Are we closer?
No.
We're not closer?
Only
Are we looking for 0.83?
Oh,
Oh, yeah.
I don't remember.
Yeah, we're looking for 0.083 is our theoretical.
I forgot about that. Hey.
Oh, I forgot we're trying to go.
Yeah. I forgot what we were shooting for. Let's add another 0.
0.08. 100,000? I was like,
Oh, it's not.
right?
Nice, Brady.
The lag. Can you not do 100,000?
Oh, the lag is real. It did in the other class.
It crashed.
I may have just crashed it.
Syria.
Equal to plus for the
Do a trillion. Syria.
Exit page.
Oh,
Syria. Greedy.
roll.
We'll try it again. It worked in the other class, so we're rolling 2 die. What were we on? We were on 100,000?
Yeah.
You grew up playing with that dice.
Lag.
It's trying. It's trying. Okay, oh. Oh. Oh.
Keep the goblins. They'll love that game. No, don't play goblins.
Okay, let's see it search. Braden.
Oh, yeah.
-4. You're
Zero.
Zero.
Wait, actually?
No, so we're going to subtract 4 from that 8,000.
So zero?
Not 0.
What? It literally says 0 out of...
No, that's lying.
So we have a total of 8,394.
No, it says 0 out of 8,000.
No, but he hasn't seen arrows yet.
You see a 4?
See how it's counting them? There's at least 2 of them.
Wait, go again. Wait, Kristen.
And then there's 2 below.
Shh, 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 shh.
No.
Let's start counting. 1.
So it is, let's count them all.
Yes.
Okay, we'll spend the rest of the year counting.
8,127.
Okay, so
No.
someone write that number down so when I come back here we can write that down.
Why write it down when you got this big brain up here?
Okay, big brain. What did we have?
8392.
8392.
Minus 4.
Minus 4 would be 3988.
Big brain can't do that.
Out of 100,000, what would that be approximately?
That's the one.
That's the one.
And not quite. There's point 3333. Not point 8888.
We're 0.084, right?
What?
Are you
Why'd you
kidding?
round?
We got to round up. Okay. All right, we're not going to do a million. If we did a million, what do we approximate is going to happen?
We're gonna pass it.
What was that, Elsie?
It would miss 8.3.
It wouldn't miss 8.3. It would get real close to 8.3. And if we did 10 million, it'd be almost exact. There is something called the law of large numbers. That with probability, and it is called the law of large numbers, is with probability, the more times you do something, the closer it's going to get to your theoretical probability, as long as your theoretical was correct. Kind of like if you flip a coin. You have a 50-50 shot of getting either one of them, right? If you flip a coin 10 times, you might get 7 heads and 3 tails. If you flip a coin 100 million times, you're going to see it's almost exactly 50-50. It's the law of large numbers that the more you do an experiment, the closer you're going to get to your theoretical probability. All right, so that is the law of large numbers. It's a good thing to remember. All right, last thing is, below are the number of points a football team scored in a season. My first question is, how many games did they play?
5.
Don't guess.
I did that wrong.
What was that, Izzy?
16.
There are 16 games that they play. Based upon those 16 games and the data provided to you, what is the probability if they played a second, maybe they made it to the playoffs, what's the probability they score 11 points?
0.
Nope.
Oh, that's number. Okay. 4 out of 16.
What was that? 4 out of 16. We have 1, 2, 3, 4 where they scored. Now we just have this. So that would be the same thing for 12, 13, 14, 15, 16. Because we have them as a group data. But according to this, we'd have a 4 in 16 chance, which is a 1 in 4. Yeah.
Wouldn't it be a 4 in 16 chance that all of the 10 through 19 points they scored games were 11?
Well,
Whoa.
I mean, it can't be 10. But, like, you have to do, like...
Well, the little
I hear
bucket
it.
thing.
Yeah.
Like, wouldn't it be, instead of being like the chance that they scored 11 points, it would be the chance that all of that bucket was just 11 points.
Right, but we're using the data that's provided to us. This is all the data we have. So based on the data that we have, this is our best guess at it.
Good try, Owen. Good try.
But you are 100% right. What Owen said is, realistically, this is 10 through 19. So the probability of them scoring 10 through 19 would be that 4 over 16. First of all, is this histogram done correctly? If not, what's wrong with it? Zach?
It's not by like the, no, wait,
Yeah, what number should be here?
10.
10. That should be a 10. We shouldn't have the groups like this. And this would be a 20, and this would be a 30, so we can actually correct this as well. But Owen's 100% correct. This really is from 10 to 19. That's our probability. But since 11's in that, that's our best guess. Our best guess on this is we have a 1 in 4 chance of getting that based upon our data. Is this experimental or theoretical probability? Theoretical?
Yeah.
So we got all the stats of all the players and looked at the team that they're playing and came up with odds that way?
No.
Or did we take data from an event? We took data from events. That automatically makes it experimental. Remember, theoretical is all about sitting down and thinking about it. You have to rank all of the players. We have this good a quarterback versus their quarterback versus this person. Why are you packing up?
Right.
I need to go.
Not only am I still talking, we still have a bunch of class left. So this is definitely experimental. It'd be theoretical if I went down and ranked every single player, came up with their pros and cons, and then kind of like the bookies do in Las Vegas. They weigh everything. That would be their theoretical probability. If I just look at 16 games and I take their points, that's experimental. And the thing about experimental is if they play another game, won't that change this data? Like say they score 45 points, that will change my data, my experimental will change. Theoretical will not change just by playing games. Theoretical could change if I change components of it. Like if I roll a 6-sided die and then I roll a 12-sided die, but that's a new set of circumstances. All right, so that is definitely experimental. All right, on your homework, I do want you to try to write, so let's look at number 1. Let's look at number 1 on your homework. It says, based upon these results, so Amanda's using a standard deck of 52 cards and selected cards at random. She recorded the suits of the cards she picked and then replaced the cards. Now, I want to note, for those of us that don't understand how a deck of cards work, a deck of cards includes an ace, a jack, a queen, a king, and then it includes number cards 2 through 10. So basically it's 1 through 10 with an ace being 1, and an ace can also be the big number, but we're not going to get into that. So we have 2 through 10 are our number cards. Our face cards are called ace, jack, king, queen, and king. Each of these cards comes in one of 4 different, actually comes in all 4 suits. So you can have an ace of hearts, an ace of diamonds, an ace of clubs, and an ace of spades. When added up, there are 52 cards because it's 4 times 13 cards. So the first question is, based upon her results, she ended up getting 9 hearts. So on the first problem, what I do want to see is I want to see you doing probability of either putting an H in there for hearts, or you can draw a picture of a heart, a kind of bad heart, however you want to, but I want to see probability. And we would go, okay, she got 9 out of 30 cards that she picked were hearts, which you can reduce down to 3 over 10. The next one asks for theoretical probability. Who knows the theoretical probability of getting a heart? Yeah. 1/4. Either we look at each of these has 1 out of 4 would be a heart, or we can go each of these cards has a heart. There are 13 of them. We can do 13 divided by 52, which would turn into 1/4. I think that's all I really have to go over with these. The rest is up to you to complete.